This is the lecture for Part A of Module 2 of Unit 4, Chemical Equilibrium. This lecture concerns relationships between equilibrium constants. In this unit, we'll look at several mathematical properties of equilibrium constants. In this module of this unit, I should say. One rule is, or one property is, that if you consider the reverse of a particular reaction, its equilibrium constant will be the reciprocal of K. For example, consider our acetic acid reaction. We know that at equilibrium, K equals H plus times acetate concentration over acetic acid concentration, and that this number, whatever these values come out to be, must be 1.8 times 10 to the minus 5. It makes sense then if we look at this from the other side, or consider the reverse reaction, the value of K would be the reciprocal of 1.8 times 10 to the minus 5, or 5.6 times 10 to the fourth. And notice this number is equal to the reciprocal of the reaction quotient for the other reaction. So reverse the reaction, and its K will be the reciprocal of K. Now let's consider a second rule. Consider multiplying reactions by 2, in which case I will show you that K gets squared. Here I've multiplied the reaction by 2. 2 acetic acids go to 2H plus and 2 acetates. The equilibrium constant for this reaction, with all the coefficients doubled, is 1.8 times 10 to the minus 5 squared, or 3.2 times 10 to the minus 10. We'll call this K2. It makes sense that K2 should be squared because at equilibrium, K2 is the square of H plus concentration times the square of acetate concentration over the square of acetic acid concentration. Or, another way to say this is that the reaction quotient for this reaction must be the square for the reaction quotient of the first reaction displayed. Alright, let's consider one property, additional property, which is if we add two reactions together, the resulting reaction will have a K found by multiplying K's together. So consider, for example, this reaction. 2 NOs plus a bromine react to make 2 NOBRs. Consider this reaction's equilibrium. Suppose we have information on this reaction. 2NO goes to N2 plus O2. K, you'll notice, is quite large, 1 times 10 to the 30th. The products are very much favored here. And consider the reaction. N2 plus bromine plus O2 goes to 2NOBr. K for this reaction is extremely small. However, you will note that if we add these two reactions together, N2 cancels, O2 cancels, and we are left with the reaction we want to know about. K for this reaction will be the product of this reaction and this reaction that we've added together. Or, in this case, comes out to, we have a typo down here. This should be 2 times 10 to the negative 27, but the answer is 2 times 10 to the 3. Alright. Now, keeping all the properties we have just learned in mind, be prepared to try the example problem. We're given two reactions. We have two K values for each. And we're supposed to find K for the third reaction. Alright, now note that you cannot find C, as in the previous example, by directly adding A and B together. You're going to have to manipulate these equations and their corresponding K values. Manipulating the reactions should produce a reaction that adds up to C, and then you will need to multiply the manipulated K values together. In practice, this is much like a Hess's Law problem from General Chemistry 1. How can C be written as a combination of A and B? Now consider, if 2CO plus O2 goes to 2CO2, with K is 3.3 times 10 to the 91, I can divide each of the coefficients by 2. CO plus half, O2 goes to CO2. And then I can take the square root of K to find the new K value for this reaction. Likewise, I could take the second given with its given K value and divide each of its stoichiometric coefficients by 2. The new K is the square root, or 3.02 times 10 to the 40th. Alright, now we're not done with this yet, though. I would like to reverse this reaction. H2O goes to H2 plus 1 half O2. And the K value for this reaction is the reciprocal of K, or 3.3 times 10 to the negative 41. Alright, now I have two reactions and their K values. And I want to add this reaction and this reaction together. When I do this, the reaction I obtain is the target reaction, the one I want information about. Here are the K values for the reactions I am summing, which I have just determined. The K value for this reaction can be found by multiplying the two K values for the reactions I am adding together. Alright, let's move on to consider equilibrium constants for reactions involving gases. Here I've written a reaction for gases. We've seen this way of writing reactions before, whereas reactants and products are capital letters, stoichiometric coefficients are small letters. We've already seen that K is equal to Q, which is a ratio of product concentration raised to exponents over reactant concentration raised to exponents. However, the concentration, moles per liter, of a reactant A is proportional to the partial pressure of that gas. In fact, you could solve for the partial pressure. It's equal to N over V times RT. And if you represent this as moles per liter, that is concentrations times RT. So, for any reaction involving gases, it is possible to write an equilibrium expression involving partial pressures, in which case you have partial pressures of products raised to powers in the numerator and partial pressures of reactants raised to powers in the denominator. Whereas Kc involves expressions of concentrations in moles per liter, Kp involves pressures in atmospheres. And the relationship between Kp and Kc is Kp is equal to Kc times RT to the power of the delta N. Delta N here is change in moles of gas. Now this expression comes from the ideal gas law. So it will be important to note that R is R from the ideal gas law. In this case, use this value of R, the one that accompanies this unit, so 0.08206 or 0.821. And the temperatures must be expressed in Kelvin. So a couple of examples. Consider this reaction. HCO2 goes to CO plus H2O. Write down the equilibrium expression or equilibrium law for Kp. If Kp is 1.6 times 10 to the 6 at 400 Kelvin, what is Kc? You should be able to stop the presentation and attempt this problem before going on. Alright, here we have an answer. The value or expression for Kp is pressure of the product species over reactants. So this is the correct expression. And Kp is Kc times RT delta N, where delta N is change in moles of gas. Change in moles of gas is 1 in this case. Start out with 1 mole of gas on the left, end up with 2 on the right, so it is plus 1. So Kp is Kc times plus 1, or Kc times RT. Or we find Kc by dividing Kp by RT. 1.6 times 10 to the 6 is divided by the gas constant, 0.08206, and by 607. The new numerical answer here is 2.9 times 10 to the 5th. I've placed braces around the expression in the denominator to note that you are dividing 1.6 times 10 to the 6 by this and by this. I have not used units in the values of R or T. The convention is that K is unitless. You have to know that if it's a Kc, you use concentrations of moles per liter, and a Kp, you use atmospheres. Note again the value of R that I have used to solve the problem. Alright, let's consider another example involving the reaction of sodium hydroxide solutions with carbon dioxide to make sodium bicarbonate solutions. This is a means of actually removing carbon dioxide from the air. The Kc for this expression would be this. The Kp, since we have one gas, would simply replace a concentration with pressure and would be written like this. And one might ask, if Kp is 1.4 times 10 to the 13th, what is Kc? Note the delta N here is negative 1. We have 1 mole of gas on the left and no moles of gas on the right. So the number of moles of gas is decreased by 1. You can attempt this before going on. When you're finding change in moles, the important quantity is change in moles of gas. There's one gas. All other species are aqueous, pardon me, I have this correct now. Change in moles of gas is minus 1. Therefore, Kp is Kc times RT to the delta N. Delta N is negative 1. Kc times RT to the negative 1 is Kc over RT. So Kp is Kc over RT in this case. That means we find Kc by multiplying Kp times RT. And we are assuming a temperature of 298, a standard temperature here. So that R times 298 is multiplied by 1.4 times 10 to the 13th, and we obtain a Kc of 3.4 times 10 to the 14th. This concludes the lecture for Module 2A of Unit 4.